Abdullah, you know that on Thursday we have the project assignment thingy. So make sure that on Thursday you are here, because I, the actual assistant of the course, will be also here, and we will discuss the project. I think we will have like 14 groups, although there are a few of you who already have assigned some work to do. So there will be like 14 groups, and then we will have like 15 topics. So even the last group will have a choice. And also, if you are not here and you know whom you want to work, you will talk with your friends to make sure that you have the group. We will make a group of 3, right? So every group will have 3 people in it. And if you don't come, if you don't have a friend after 1 month, then I will make sure that you will have a friend. I will assign you to a group, and I will assign you a project. So, so I'm telling you, if you don't come, it means that you permit me to do it. This is one thing. In the module, I have opened a block called project. And inside that block, you can see that we have template of the report, template of the project. It's in LaTeX. Do you know LaTeX? Is there anyone who doesn't know LaTeX? Good. So this is a good moment that you go and learn. You will learn how to write the report. Although for the report we have also the Word format, but for the poster I have it in LaTeX format. It's actually IEEE format. Now what I want you to do is this. The template that I provided for you is A0. I mean, you can close your computers. Yeah, close your computers. Thanks. It's in A format of A0. However, the poster that you will make would be A2 or A3. You decide. Now, for the poster, you have to print out the poster, which means that you have to pay. So it will be like 10 euros maybe, but you are 3, so everybody will pay 3 euros and 30 cents, right? And I will collect the posters at the end of the semester. 1 poster per group, so you don't need to print 3 posters. If you can do it in A2, do it in A2. If you cannot, do it in A3. There is no point that you make the font size to be 300 to fit it into A2 if you don't have text or some information, right? So make it, because it has happened before, people had a big poster, as it says, it looked like a political advertisement. So it was just 1 picture and 1 title. So this is not how the poster looked like. You can see the template, so you understand what you have to put in there. Similar thing for the report. About the deadlines, we will talk about it. However, the poster presentation with high probability will happen like one of the last day of December. So you will do the poster presentation and you will do the defending of your project. However, the submission of the reports and code and so on, I usually give the time till end of the final exam, which is like about 15th of January. So practically, because you will be evaluated basically by your presentation. In other words, after your presentation, you cannot really, of course you can go and improve your code, but it will not affect on your grade of your project. What it will affect is only the report part that I will evaluate. Again, you do not need to submit 3 reports. A group will submit 1 report, and the point of the report will be equally distributed. However, the point of the presentation, as I stated before, they can be very different. 1 person in a group can get 0, 1 person in a group can get 100 out of 100 of the presentation. Like you will be assessed individually. And as I said before also, we will have a jury. So it's not like I like you, so I might be biased, and I don't like you, and I might be biased. I will have a jury of people who absolutely you don't know them, they don't know you, so they will be unbiased, and I will average the total point. In the past previous years, it happened that my points and their points were very correlated, although I'm quite known for giving high grades anyway. So, so these are the things that we need to know. Okay, so I will fix the dates of the presentations and so on also. And again, you might know that I am a person who doesn't change his word. So if we fix the date, it is the date. Now what happens, this has happened before with PhD students, that in the day of the presentation, they have to be in a conference, for instance. These are a valid exceptions, and I understand, and usually they will do the presentation before. So they don't have time more, they actually have time less. Or if something happens and you are ill and so on, we try to kind of compensate it. But apart from that, no other excuse is acceptable. You are not appearing in there, it means that your point of presentation would be 0, right? So this is another thing related to the project. I think I don't have anything particular to say. We will talk a lot. We will have all Thursday about the project. So then this is good to go and think. Although I will give you the topic, feel free to propose your own topic. So if you have made your group and you have your topic, it will be good to let me know in advance. Some of you have done it. Many of you, I rejected it. But in general, it will be good if you can contact me in advance so we know that what you have. If not, on Thursday you can tell me your topic and we can discuss and I can accept or I can decline it. There are 2 reasons that I decline. One is that it can be way too simple or it can be way too complicated for a course project. At the end of the day, this is a course project, it is not your thesis. You may continue later and do your thesis out of it, right? But I cannot really, it will not be fair for some of you that some people will put too much effort. It will be good if you do, but I don't expect it's a course project, right? So, and the project that we are giving, the topics are being selected that they have almost the same level of difficulties. So I do not accept an argument that somebody's topic is easier than somebody else's topic, right? And what might happen is that if there is one topic and there are 3 groups who want that topic, we trust the luck. We just do like a lottery, who will win, right? Okay. Now we can start our lecture. What we did before, till now, we enhanced, is it recording? What we did before till now, we improved the quality of the image, we enhanced the image, we call it image enhancement, and we did it in the spatial domain. What it means, a spatial domain, it means that actually whatever you were doing on your image, you could immediately see how it affects on the output, right? And we remember that when we wanted to do something in a spatial domain, we can do it either pixel-wise or point-wise, or neighborhood-wise, right? Which means that you can, you are picking up one pixel and evaluate it, you don't care about what is around it, or sometimes you take a whole neighborhood, you look at everything in order to say what is the new value of that specific pixel, right? And you remember we did lots of convolutions, correlations, all the filters, things that we have seen in the last lectures was about that one. What about the pixel-wise operation? When do you remember an example of pixel-wise operation? Abdullah, do you remember? Who remember an example of pixel-wise operation that we did?
Like increasing luminosity?
Yeah, change of illumination, histogram equalization, or any way of change of contrast or illumination is a pixel-wise operation because you give pixel 120 or 138 calculates and tells that it should become 64, right? It was like calculating. It didn't care about what is happening about your neighbor, right? So now, no matter which one we were doing it, we were still in the spatial domain. In other words, we were taking one of the pixels of Lena or its neighbors, you calculate and you put it back. So you could start to see the details of the hair, or you could start to see the faces blurred, or you could start to see the edges of the image. Another way of manipulating the image or enhancing the image is that we leave the spatial domain to another domain and we do the work in that domain. But because we as a human can see everything only in the spatial domain, so it means if you go to another domain, you have to get back to your own domain, which is a spatial domain, in order to be able to see it. It doesn't mean if you go to another domain, you cannot see it. You can see it. We will see actually lots of examples of that one, but it won't be meaningful for you. It has different interpretation. Now, what we are doing in general, I gave this example on the last lecture, it was like this. We have a marker, which, as you can see, this black marker, it looks like a rectangle, right? It looks like a rectangle. So what I'm doing is I'm just changing my point of view. Let's do it like this. So what you see a circle, right? It didn't change the nature of this black marker. It's black marker, and in particular this one, it was an empty black marker. It doesn't matter from which direction you look at it, the properties have not been changed. However, what you see is changed. So this is the whole thing. Instead of having a long rectangle, I have a very small circle, right? So it means that maybe manipulation of this one would be easier. Let's open the windows. I'm a bit fat, so I just wait a little. Yeah, yeah, I mean it was the dead marker. So this is the whole thing that we want to do. We want to go to a new domain, which we call it a frequency domain, and if you take an image, a frequency domain, it's still the picture of Lena. It is still your image. It may not look like that long rectangle that you had. It might be a circle, but it is still the same thing and it has the same properties. So let's see that there's a little bit of history. What was this frequency domain representation? Some of you might have taken the course called DSP or signal processing, or maybe in the mathematics or advanced mathematics you have seen we have something which is called Fourier transform, right? Fourier transform. And again, it's just a name. We don't really care much about the math behind it. There goes the math. Fourier transformation. It's a mathematical transformation, right? Which was introduced by the French mathematician called Fourier. And what he said was this. He said that any function that you have like this, it can be written as addition of infinity many sine and or cosines, right? So it means that in order to create one straight line like this, you have to add lots of sines and cosine, and if you do it, they cancel each other and so on, and as a result, you will get a straight line. So this was a very big boom. Why it was a very big boom is this. In general, we know that if you want to draw a particular sign, the only thing that you need to know is the frequency. If you know the value of the frequency, because time, if it is known, because the time is always from minus infinity to plus infinity, you can draw it, right? The only thing that changes this sign with this sign is the frequency, and of course a constant which you can multiply. You don't care about that constant, right? So it means that this is very good. If I can represent any function or any signal with addition of lots of sine and cosine, it means that every sine or cosine is corresponding to one frequency. So it means that any function that you give me, any signal that you give me, while using Fourier transform, I can tell you that what frequency I have in there. What frequencies I have in there. Did you get it? So let's do a simpler example. Do you know this function of sine x? Right? And let's call it even sine 2 pi x. Sine 2 pi x. This is a function which is continuous with plus minus from minus infinity plus infinity. This is a function that has a frequency of 1, right? If I want to write this one as addition of infinity many sine, what do I get? If Fourier wanted to write this one as addition of infinity many sines and cosine, what do we get? Yeah?
The same.
Yeah, itself, right? Yeah, this is addition of this function by itself. I mean, like plus 0. So it means that luckily we already have sine in it. And how many frequency do I have in here? Only one, which is frequency number 1. In other words, I can go to something which is called frequency domain. And I can say that this function has only one value and it is number 1. Because I don't have any other frequency. And so in the frequency domain, when you look at only number 1, you understand that you have to draw sine 2 pi x because it is frequency number 1. Now, because we are drawing the magnitudes in general, everything has a symmetry. So in other words, if you have number 1, you also have number -1 as well. But we always look at the positive one. Right? So, what about if I have I don't know how it looks like, a function which looks like this, and I tell you that this is an imaginary function. It might not look like this, it's an exaggeration. So it's like 2 pi x plus sine 4 pi x plus sine pi x. So let's say that this is a function which is addition of these 3 sine. So if we are applying Fourier, it means that this function can be written as addition of these 3 sine which we already have it. So what are the frequencies that we have in here? We have 1, we have 2, you just divide it by 2 pi. And we have 1/2. So it means that if I go to Fourier domain, it is like that I have 0.2, half, then I have 1, and then I have 2. And obviously I have also the negative ones too. I don't have any other value. I don't have the value, in frequency domain, I don't have the value of 2.5. Why? Yeah, because there is no 2.5 frequency in here. Right? If we had it, we will write it. If we had it, we will write it. Now, did you get the concept? But Fourier is a more complicated formula because it says that even if you give a straight line, I will tell you that what would be the representation in frequency domain. For us in this course, we don't use the formula. We already either I provide you what the representation is, or you have a table in front of you which you can always see. Or in your practical, you are using a command like FFT2 and it does the Fourier representation for you. Right? But it's important to understand what happens. Now, there are a few important things that you have to know. Let's stick with 1D, then we talk about image. So, we have time here, we have frequency. In case of 2D, you have the spatial domain in here, and you have frequency domain in here. If something is discrete, what is its effect in frequency domain? Continuous. What else? If it is discrete in time, it will be
Discrete and frequencies.
maybe. So this is continuous, this is discrete. Abdullah, you should also know. Sorry? Zero. It will be periodic. If something is discrete, it means that it will be periodic. What does it mean it will be periodic? Claude, what does it mean something is periodic?
It will appear again after.
Yeah, it means that there is a block which will start to be repeated everywhere, right? It will be start to repeat it everywhere. Like this, in this case of sine, you take this block, which is one oscillation, and then it will start to be repeated in infinity many times, right? Infinity.
What is the base? So what would be its frequency? It's 1 or something like that?
Sorry?
What would be its frequency?
If something is discrete, then it will be periodic function in frequency. For example, it might be this pulse, then it means that it will be repeated. Right? And if it is periodic in time domain, what happens to frequency domain? It will be discrete. It's called duality property. In case of image, instead of time, we use the word spatial, right? So if it is discrete, we get periodic. If it is periodic, we get discrete. Now, in this course, we are dealing with the digital images, right? We are dealing with digital images. So if we go to the frequency domain, what do we see? Sorry? I don't hear you. Yeah, what we will see one specific block which will start to be repeated. Now, look at the picture of Lennon. It is limited, right? It starts from one specific pixel, it finishes with one specific pixel. But if you convert into the frequency domain, what we will see is that you have some representation which is everywhere. Although because it is periodic, we will only look at one period. But it is everywhere. Keep this one in your mind because we will get back to this sentence a couple of times. I mean, I've asked this question from you a couple of times. Okay? So, because we have a digital image, it means that whatever we do whenever we go to frequency domain, you will see that it will be periodic. The block will be repeated. So, let's start our lecture after knowing this little bit of the story. What happened is that we have a Fourier. Fourier said that if you give me any signal, I can tell you that this signal is addition of infinity many sines and cosines. In some cases, they are finite, like this example, like the examples that we did on the board. And the reason that sine and or cosine is very important for us because, Abdullah, one sine or one cosine can be represented only with one frequency. So it means that if you give me any signal, I can tell you that what are the frequency inside this particular signal or image and so on. Now, a little bit of mathematics. I quickly go over them. You are not responsible for any of these slides that you see or these formulas. In general, in 1D, this is the formula that we are using in order to find the Fourier representation. You know that this is integral, right? And if you have the Fourier representation, you can find the inverse of that in order to come back into time domain, right? And in case if we have discrete, what is the equivalence of an integral in discrete? Summation. Then we will start to have a summation. Here is an example that we have a sine function. We have a sine function, and this sine function has only one frequency. That's why that you can see only one impulse. We know that because it's a magnitude, then it means that it has symmetry, so we have the same thing in the negative. But usually you only display one of them. Here we have a Gaussian. We have a Gaussian, and when we come to the frequency domain, what do we have? A Gaussian. This is a very, very important property of Gaussian. If you are Gaussian in time or in spatial domain, you will be Gaussian in frequency domain. This is something that usually I ask you in the exam. I mean the conclusion that you get from it. What is the other name for Gaussian distribution? Hans, have you seen Gaussian distribution?
The bell curve.
Yeah, the bell curve. What else? Mexican hat, right? But it has one particular name. We call it
Normal distribution.
normal distribution. Why do we call it normal distribution?
Many things appear like that in
Because in the normal life, this is the distribution that we see a lot. Right? This is a distribution that we see a lot. If we do an exam, this is what we expect to see as a result. This is what is expected to be seen as a result. Right? Now, this is very important. Keep it in your mind. In the real world, normal distribution happens. If the distribution is not normal, it means that what happened?
Depends on what you can say, skewed or
If it is not normal distribution, what does it mean? Some external force has happened and it forced our distribution to be skewed or to be whatever it is. So, in other words, if I do an exam, a normal exam, and the distribution is not like this, it means that maybe the students were cheating if they decided to go too much towards the 100, right? In other words, this is a very important thing to understand if some external forces has been happening over the data that you have been collected, the normal or natural data that you have been collected. So that's why that we spend lots of time on Gaussian and we talk a lot about the Gaussian. It's normal, this is something that we are expecting to see, and if you don't see it, it means that somehow some external force has been applied over your data. The other one is the sinc function. Do you know the sinc function? It's, for those of you who don't know the sinc function, it's a function that we define it. We write it as a sinc x, which means sine x over x. In some book they write it sine pi x over pi x. Let's consider as a sine x over x, right? Sine function divided by x. It's a function that we use it quite frequently in any signal processing course, in this course a lot, but this is a function that does not exist. Right? It's a function that we wish it exists, but it does not exist. Why it does not exist? Dush, why it does not exist? Do you know this function? Why it doesn't exist? Simon, have you tried to build it? Have you tried to produce it in the electric lab? No. Has anybody tried to build it in the electric lab or any lab?
for 0 it goes to
Yeah, it doesn't exist because at 0 it divides by 0. You might have tried it actually in your life quite a lot. It's called the short circuit that you're producing sometimes. Huh? We wish it exists. If let's assume if it exists, it means that we wouldn't have an energy problem in the world. Because we have an infinity amount of energy when you are dividing it by 0. So it does not exist. However, it's very pretty and mathematically you can produce it. This function is not periodic because you can see the shape of this function. It is not periodic, but it has lots of periodic property. We know exactly where the zeros happen and the distance between zeros are all known to us. So it's not periodic because as you can see the magnitude is decay. However, where the zeros are happening, we know them. Right? We know them. Why do I know where the zeros are happening? How do I know the zeros, where the zeros are happening? Alex? How do I know where are the zeros?
Check the zero.
Sorry?
Check the square wave it's in the 25.
I know that from the picture, I know that I know. But how do I know that I know?
Degree.
Yeah?
Because it's only zero when the sign does.
Yeah, it zeros when the sign is equal to 0, and I know where the sign is equal to 0, right? And 0 of the sign are happening periodically, so the zeros are happening periodically. Now, these wrinkles are called the wing of the sinc function. The wing of the sinc function. And as you can see, the magnitudes actually start to decline very quickly. And theoretically, on the plus or minus infinity, this magnitude is already 0. The magnitude is already 0. Now, if you have a sinc function in time domain, it means that if you go to frequency domain, you are getting this box. You are getting this square wave. And because in Fourier transform we have something which is called duality, it means that in the time domain, if I give this one, I will get the sinc as an output. So, do we have sinc? Do we have sinc? Arun? Do we have sinc function?
In time domain.
I don't know, in any domain.
In reality, no. But
No, so we don't have sinc function. So if you don't have sinc function, because the square function is just one other representation of this, so it means we never have this function. Remember, these two are the same thing. You are just looking at it from different, it's like that we are looking at it from different point of view. If one of them doesn't exist, this one doesn't exist. Do we have this signal in the real world?
Never perfectly square.
No, we can never produce. In other words, the word is analog. You can never go from 0 to 1. You might have this rise very sharp, but you always have this rising period, right? You always have this rising period, right? Because this doesn't exist, this doesn't exist, this doesn't exist, the other one exists. So it's a duality property. And this is another very important thing that I will get back to you and I'll ask a question about that. So here you can see all of them in one picture. If in time domain, if you have box or a square, you get sinc. If you have sinc, you get a square. If you have Gaussian, you get Gaussian, right? When we come to the concept of digital signal, which is 2D, the integrals, because it is digital, will turn into summation, and because it is not one dimension, we have two dimension, then it means that we will start to get. Let me show you first. We start to get a double summation, right? I don't ask the question of the formulas. I'm just putting it there for you to show that this course can be very mathematically equal. But let's talk a little bit about some other important things in this Fourier representation. When we are representing a signal or an image from time domain to frequency domain, we are actually representing it by using two terms. One of the terms is called the magnitude, the other one is called the term phase. And what we care in this course is the magnitude of this Fourier representation. And the magnitude of Fourier representation is calculated, if mathematically you want to calculate, because it's a complex number, is calculated by imaginary part of the square plus the real part of the square. Again, because you don't know the complex number, or even if you know, we assume you don't know, so you are not being asked to calculate it. In the practical, you will see that